Hello everyone, and welcome to this video on section 4.1 called Basics of Differential Equations. In this video, I'm going to be taking you through a sample version of a Newton-Alta assignment for this Basics of Differential Equations section. And please understand that the questions I see in this video may not be the same exact questions you see when you work on the assignment yourself. But the objectives are the same, and problems will be hopefully similar enough that watching me do them here will help you when you work on them on your own. Okay, so here it is, the sample version, preview version, right? You won't see the word preview when you work on it on your own. Got the title of the section. Your mastery bar in the upper right-hand corner tells you how far along you've gotten. You have your activity log, shows you all the objectives, right? Looks like there are 5 objectives, and I have it toggled so that you should be able to move back and forth between the bold headings, right? So there's general solutions to differential equations. Then we have initial value problems, which I can start at any time if I wished, but I don't think I'll be using that. Then you have a current objective. Underneath that, you have a question related to it. And at the bottom of every question, you should be seeing a feedback button. So you can send feedback directly to Newton if you see any typographical errors or problems with the answer explanations or something that's not right. Send them feedback and hopefully they can fix it. You will not have this instructor cheat button, right? That's for instructors only. But you will have a more instruction button. So if you're struggling with a particular topic or a particular objective, click on this and you'll be taken to a page with some further reading to do or videos to watch or both. And then you'll be given questions, related to that instruction. And you can work your way through the assignment that way. You can do this for every single problem. Okay. All right, so the first objective I'm looking at here, solve general solution problems for linear differential equations. And this question, we're given instructions. Use integration, right, to find a general solution of the differential equation below. So remember, a differential equation is an equation involving functions and their derivatives. And a solution to a differential equation is a function that will satisfy such an equation, right? So you're not looking for numbers, not numerical solutions, but functions. So here I have dy dx, right? Y prime, the first derivative of y, and it's implied here that y is a function of x, right? Y is the dependent variable, x is the independent variable, equals pi times the cosine of pi x over 4, or pi over 4 times x. So I'm going to write this out, and we'll go about finding, y equals. We're going to find a function, y as a function of x, that would satisfy such an equation. All right, so let me write this out. So the equation is this, dy dx, right? First derivative of y with respect to x equals, pi times the cosine of, it was pi x over 4, but I'm going to write that as pi over 4 times x, right? Same thing. Now, like I said, this is the first derivative here, right? That's dy dx. So you could also think of this as y prime equals, pi times the cosine of pi over 4 times x, or pi x over 4. So this is a very simple differential equation is just telling us, the derivative of this y that we're trying to find is this function of x. Right? Again, the independent variable here would be x. Everything's with respect to x over dx. Well, if that's the derivative of y, to find y, I would just simply need to integrate, right? Take the indefinite integral of both sides. Now the integral of a derivative is, you're back to the original function y over here. And then we just have to now, find the indefinite integral of, the function of x on the other side, pi times the cosine of pi over 4x. And of course, this is all with respect to x. Right? This is a function of x. Okay. Now, if you want, you don't have to do a substitution here, but I will. I like having just cosine of a single variable, not like some multiple here. I'm gonna make a little sub, have u replace this pi over 4x in here, and then du would be pi over 4, times dx. So dx, right, when I replace this, dx would be 4 over pi, solving for dx here, times du. All right, so I'll make these replacements, these substitutions, and we'll have the integral of, pi times the cosine of u, right? Again, this expression inside I called u, times, and then dx we're seeing is 4 over pi times, du. Okay, so that's nice. The pi's will cancel. I got pi over pi. And this is now just 4 times the integral of cosine, which is 4 times sine. Right, so this is 4 times the sine of u. And then now that I've integrated, let's sub back. All right, go back to the original variable. The original independent variable was x. And we get this 4 times the sine of, u was, pi x over 4, or pi over 4 times x. Now remember, this is an indefinite integral. So I could also throw on, any constant I wish, right? So again, c here plus c. C is any constant, plus 2, plus 8, plus pi, plus the square root of 2, minus 1/3, whatever. And it would still have the same derivative. So there we go. Y equals 4 times the sine of pi over 4 times x, plus any constant would be a solution. That's a u, sorry. Would be a solution of this differential equation, right? And since there's this, description of infinitely many here, we have our general solution that they're asking for, right? Describe all of them. Now, if you'd like to check, and I'm not going to do this for examples after this, but if we want to check our answer, just substitute stuff into the equation. Now, all I need to do here is replace y prime. Right? This is y, find y prime. Right? Y prime would be, 4 times the cosine of pi over 4 times x, but then, you got to apply the chain rule here. Multiply by the derivative of the expression inside, that would be times pi over 4. And then you see the 4's canceling, and I do get the expression on the other side, right? It would be pi times the cosine of pi over 4x, or pi x over 4. So the left side and the right side would be the same. This, for any constant c, this function here, y equals 4 sine of pi over 4x plus any constant, does satisfy our differential equation. All right, so like I said, I'm just going to do this For the first example here, I won't be checking solutions too much unless I really feel the need to in future problems in this video. All right, so this is what we're entering right here. All right, so I'm going to go back to the assignment, and we have y equals, so that was 4 times the sine of, pi. There should be a symbol for pi here. Pi x over 4, pi over 4 times x. And again, don't forget, this is general solution. You're doing some sort of indefinite integral here, so don't forget the plus some constant at the end. If you don't write that in there, you're just going to be giving one solution, not a description of all of them. And they want the general, right? A description of all of them. All right, let's submit. Wonderful. And after every question, after you submit an answer, you'll be told if you're correct or incorrect. Maybe if you're incorrect, you might be given a second chance to fix things before they really say you're wrong. And then you'll have an answer explanation. I would highly recommend reading through these, especially if you get it wrong. See if you can figure out where you went wrong. I would even read through them, just glance through them if you got it right as well. Because, they may be doing something that you didn't think of that makes things easier, and you might want to try for future problems. Okay, well, let's continue on. All right, so once again, I'm still in this same objective here, right? Solve general solution problems for linear differential equations, and they're very basic first order, right? First derivative linear equations, where I just need to do, indefinite integrals, right? Antiderivatives. So let me write this one out. We're again solving for y here, finding a function y of x, right? We got y prime equals x minus 3 times the natural log of x. Okay. And once again, y is implied to be a function of x here if, the other variable is x. And integrate both sides with respect to x, we're going to get the following. Y is going to be equal to the indefinite integral of this x minus 3 times the natural log of x, and then with respect to x. Now, x is no problem. That's half x squared, right? Minus 3 times. Now, I'm putting parentheses here. If you go back to my videos with the Newton-Alta assignments, it was in the section 3.1 video. We talked about integration by parts, and when you're integrating the natural log function, you can do it by parts. Select a u, have u be the natural log, and dv be just plain old dx here. And then, go through the integration by parts. It ends up being this, x times the natural log of x, and then minus x. Okay, so I'm just going to use that. We're not going to do the parts over and over again here. So my second term here, I got minus 3 times, the antiderivative of natural log x is this thing, right? This x times the natural log of x, and then minus x. And of course, I'll distribute the negative 3 here, and we get the following. We have half x squared. Then you got plus 3x, right? You have negative 3 times negative x there, plus 3x. Then minus 3x times the natural log of x. And now I'm done integrating here. We throw on any constants, right, that will also work, have the same derivative, and here we go. There's a description of any function I could replace y with in this equation, and, and it'll have this x minus 3 log x as a derivative. All right. So this is what I'll be entering in the assignment. So we had, 1/2 x squared, then plus 3x, minus 3x times the natural log of x, and then of course plus some constant. Double check that I typed what I wrote on my paper and submit. Great. All right. And again, please take a look at the answer explanations. Moving on. All right, so they've switched objectives on us. Now it's identify basic elements of differential equations. All right, so this question is just asking us to verify that a given function, so see y is a function of x here, verify that that is a solution to the differential equation below. So if you recall back in the first example from this video, I checked to see if something was a solution, some function was a solution. Well, you're just going to be doing a lot of substitution and seeing if, you have a true statement. Is the left expression on the left side the same as the expression on the right side after I substitute values for y, functions for y and y prime? All right, so I'll write out what they have. So they're asking, is the following function, y is some function of x, y equals 5 times the square root of x minus 1, which I could think of as 5 times x to the 1/2 power minus 1, same thing. Is it a solution? Sorry, this should be two separate words. A solution uh, to the differential equation. We got negative 3 times y prime minus 1 on the left side equals negative 15, times the square root of x, or x to the half, then minus 3y, plus 7. And then the last term on the right side here is minus 15 divided by 2 square root of x. All right, so that's the question. So we're going to make the substitutions we need for y and y prime. Now, y is this, right? So I'm going to replace y on the right side here with this quantity, 5 times the square root of x minus 1. So that'll replace y. Now I also need a y prime. All right. Now if that's y, y prime would be using the power rule, 5 halves times x to the negative 1/2, which I'm going to rewrite with a square root involved. All this other stuff has the square roots involved. And that's it, right? Plus nothing. So another way to write this would be 5 divided by and then 2 times the square root of x. Remember, x to the negative half would be 1 over x to the half, and that would put x to the half or the square root of x in the denominator. All right, so this is y prime in terms of x, and I'll put that in for this y prime on the left side. All right, so now I make these substitutions and then we'll check, are the left side expression and the right side expression going to be equivalent? So on the left side we have negative 3 times y prime, but y prime in terms of x, I'm going to get everything in terms of x, is this 5 over 2, square root of x. And then we have a minus 1. And I'll do some simplification with that in a second, equals. On the right side is negative 15 times the square root of x minus 3 times, and then y is this quantity, right? 5 times the square root of x minus 1, right? That's y. And then you have the rest of it, plus 7 minus 15 divided by 2 square root of x. Okay. Well, now I gotta over here distribute this negative 3, right? And I'm just gonna skip to the end here, combine some like terms. On the left side, negative 3 times this 5 over 2 root x, that would just be negative 15 over 2 square root of x. And then you still got this minus 1. Okay, so there's the left side. Then the right side, So you see, after distributing this -3, you'd have negative 15 root x minus another 15 root x. That'd be negative 30 square root of x. And then we have -3 times -1 is positive 3, which plus the 7 would be plus 10. And then you have the minus 15 over 2 root x. Okay, now look at these expressions. I mean, you know, they both have this negative 15 over 2 root x term, sure, but then the rest of it is different, right? These are not always equal then. Okay, so I'm going to put a little not equal. That means that this function we were given is not a solution to the equation, the differential equation we were given. Right, so this is not a solution. So back in the assignment, right, simple multiple choice, no, right? The answer is no. Great. Again, please look through the answer explanations. Oh, I see what they did. They added the 3y prime over there. So still no solution. Right? Not a solution. All right, next. So it's the same problem as last example where you're asked to identify basic elements of differential equations, and we're given a differential equation, something involving a function called y of x, and then its derivatives, right? Just y prime here. And we're asked to determine if a given function, y equals 3 times e to the 3x is a solution, does it satisfy this equation? So there's just a lot of substitution and checking, is the expression on the left the same as the expression on the right? All right, so is y equals, 3 times e to the 3x a solution of the following differential equation? -48 times e to the 3x minus 2 on the left side, and that needs to be equal to -2y plus 3y prime, and then plus 1 on the right side. All right, so I've got y already. I'm going to get everything in terms of x and see if we have the same thing on both sides. So I already have y. So that's going to replace this y here. But I also would like to, again, get everything in terms of the independent variable x. I need to replace y prime as well. Now, if this is y, then y prime, right, the first derivative with respect to x would be 9 e to the 3x, right? It'd be 3 times e to the 3x and then times 3 again from the chain rule. Right, so this 9 times e to the 3x, that's going to go in for y prime. All right, so let's make these substitutions. Now on the left side, there was nothing to change, so you got -48 e to the 3x minus 2 equals, and then over here, -2 times, and again, replacing y with 3 times e to the 3x, then plus 3 times, and then replacing y prime with 9 times e to the 3x, and then you have this plus 1. Now, after putting stuff together on the right side there, we got -48 e to the 3x minus 2. This would be -6 e to the 3x plus 27 e to the 3x, right? 27 plus -6 would be 21 e to the 3x, and then you got the plus 1 at the end here. So very clearly, the expressions on both sides here are not the same. And no matter what manipulation I do, I can't see how to get these to be the same here. All right. So again, these are not always equal. So the answer to the question, right, is no again. That function I was given does not satisfy this equation. All right, so back in the assignment, toggle no. All right, wonderful. All right, so hopefully they give me some examples where it does work so you can see when things actually work out. But for right now, nothing doing. All right, moving on. All right, so now we're back to like the first couple examples from the video, solving a first order equation, right? Something with just y to the y prime, right? First derivative. Now, in those first examples, y prime was alone, it was solved for, and then I just integrated afterwards. So I need to kind of do that here, right? Get y prime alone, and then you'll have some, some expression with the independent variable x on the other side. And then if I know what y prime is in terms of x, I can then just integrate to get y in terms of x. All right, so let me write that out. So we're given y prime minus x equals -2 times e to the x. Yeah, simply add x, isolate y prime here. So y prime is, -2 e to the x plus x. And now if I have the derivative of y with respect to x, I can find y itself by just doing the integral, right? Indefinite integral with respect to x, of course, right? This is -2 e to the x plus x with respect to x, right? Times dx there. And simple enough, right? These are some nice easy terms to integrate. This would be -2 e to the x plus, 1/2 x squared. And then, of course, indefinite integral, right? I could throw on any constant and we'd get another solution, right? +2 plus 3. We'd get something with this that would satisfy our initial differential equation. So here we go. This is what I shall be entering. So we had -2 e to the x, then plus 1/2 x squared, and then don't forget your plus constant for the general solution, right? You had an indefinite integral. Great. Okay. So moving right along. So another one where we have y prime alone, dy over dx, right? The derivative, first derivative of y with respect to x alone on one side, and then some function of x, some expression with the independent variable x on the other. So just like the other examples in this objective, I'm simply going to integrate both sides with respect to x, and we'll get our general solution to the equation. So I'm just going to write y prime, right? They had dy over dx. Right? Y prime is 3x cubed plus 2x squared, and then I integrate, right? That's what y prime is with respect to x. I integrate with respect to x to get y, right? So the integral of this 3x cubed plus 2x squared, right? Dx. Don't forget your differential when you integrate. And we just go term by term, simple power rule thing here. This would be 3/4 x to the fourth plus 2/3 x to the third. And then again, indefinite integral, so I can throw on any constant and get another function that would satisfy this. So y can be anything that looks like this and would have that derivative. So let me enter that. 3/4 times x to the fourth power plus 2/3 times x to the third power, and then of course plus any constant, right? Plus c at the end. Wonderful. Great, so that first objective is finished, right? A lot of just simple integration. Now be careful. The problems I saw here in the video had some nice easy integrations. Maybe that one with the natural log, you'd have to do by parts if you forget what that is. But just be aware that you may see some where you have to do integration by parts, or you might have to do a trigonometric integral from section 3.2. You might have to do a trig substitution from section 3.3, or a partial fraction decomposition from section 3.4. If you look back at all those chapter 3 Newton-Alta assignment videos, you might have to do those in some of these problems. I just didn't see them here. Okay, so just be aware. All right, moving on. So now we're just going to go till we finish off this objective. And again, we're given a question where we're just asked to verify that if something is a solution to an equation or not. So we're given some function y of x, right? And oh, this equation is a second order equation and involves the second derivative of y. And we're asked to see, is this equation satisfied by the function we are given? So let's see. So that is y equals -3 times the cosine of 2x a solution to the following differential equation. 12 times y plus 3 times y double prime, right, the second derivative, equals 0. All right, so I've already got y. There's this -3 times the cosine of 2x. That's going to go in for y. I need to fill in y double prime now. Now, if this is y, we can get y prime, right? The first derivative would be -3 times, remember the derivative of cosine was negative sine, so it'd be +3 sine of 2x, but then times 2 because of the chain rule, right? So it'd be +6 times the sine of 2x. Right. That would be the first derivative. And then the second derivative, that would be 6 times, and then the cosine of 2x times 2, that'd be 12 times the cosine of 2x. Right. Now I've got the second derivative, y double prime, that's going to go in here. Right. So let's make these substitutions, get everything in terms of the independent variable x, and see what we got. So we got 12 times, y. 12 times -3 times the cosine of 2x, and then plus 3 times, and then y double prime I have here, 3 times 12 times the cosine of 2x. And is this equal to, 0? Absolutely. Look at this, right? You got -36 cosine 2x plus 36, +36 cosine 2x. So you got 0 over here. Those would, these are opposites. Those would make 0 when you add them. And now I have 0 on the left, 0 on the right. Yes, right, the exact same expression on both sides. So this y equals -3 times the cosine of 2x is a solution of this equation. It does satisfy it. So now we finally see a yes for one of these questions. Great. All right, moving on. So another one here where I'm asked to just make some substitutions, and verify, or determine if the function we're given is a solution of the equation we're given. So here it is. We have, this question is y equals the natural log of 3x to the 5th power, a solution of the following equation. We have x to the 6th times y prime, right? So I need the first derivative, plug that in here. And is this equal to, 5 times e to the y power? So this expression for y is going to go in this power here, divided by 3. All right, there's the question. All right, so like I said, you already have y, right? This natural log of 3x to the 5th is going to go in this exponent here. We'll have e to that power, and that's going to be nice. E to a natural log, they'll kind of just undo each other, right? Those are inverses. And now I just need the derivative y prime, right? So y prime, remember the derivative of the natural log of something was 1 over that thing, right? So 1 over 3x to the 5th. But then times, chain rule times the derivative of the thing inside, that would be 15x to the 4th. And doing some cancellations here, 3 goes into 15 5 times, so I have 5 in the numerator. X to the 4th over x to the 5th would just be 1 over x. So that's just 5 over x. Okay, so this 5 over x, right, y prime, that's going in here. So I make those substitutions, get everything in terms of x, in terms of the independent variable, and we'll see. So I make the substitution. So we have x to the 6th times, and then y prime we saw was, 5 over x. And is this equal to 5 times e raised to the natural log of 3x to the 5th power, and then this divided by 3. Right? Now the left side, x to the 6th over x, that's just x to the 5th. So this is 5x to the 5th on the left. And then we have 5 times, and then here, e raised to the natural log of something is just that thing. So it'd be times 3x to the 5th over 3, and you see the 3's canceling here, and look, both sides are the same. 5x to the 5th equals, after canceling the 3's, you'd also have 5x to the 5th on the other side. Check. Yes, right, this is another yes. The function we were given does satisfy the equation we were given. So yes, wonderful. All right, moving on, continuing still in the subjective. Now this is simply identify the order of the differential equation below. All right, order is simply what's the highest order derivative you see in the equation. So cosine of 2x, that has no derivatives. Negative tangent of 2x doesn't have a derivative, but then you have times y prime. So there's a first derivative. So this could be a first order equation, but let's continue. Plus the natural log of 4x, no derivatives there. And then you see this y with the 4 in parentheses above it. If the power, it looks like a power, but if it's in parentheses like that, that means it's a derivative. So this is the fourth derivative of y. So I see the first derivative of y and the fourth derivative of y. The highest order derivative is the fourth derivative. So they would call this a fourth order equation. So order equals 4. And that is all we are being asked for in this question. Great. So yeah, those should be simple. And again, they define to you the order, if you look through the answer explanations, the order of a differential equation. Yeah, so these questions where they ask you to identify the order of an equation, hopefully they are pretty simple and you can get through them quickly. All right, so now we got 3 more objectives. Let's move on. So now we're asked to solve applications of linear differential equations. All right, so this looks like a projectile motion application where something's launched or thrown into the air, and it goes up so high and then comes back down, and it's being pulled on by gravity, right? The force of gravity. All right. So a model rocket is launched upward from a height of 9 meters above the Earth's surface with initial velocity of 58 meters per second. and the only force acting on it is gravity. All right, so we don't have to take into account wind resistance or anything like that, just gravity. The model rocket has a mass of, 0.09 kilograms, and the gravitational constant, which is what we'll start with, this is acceleration. This is the acceleration due to gravity, is negative 9.8 meters per second squared. So what they're telling us here is that anytime you have a downward pull or a downward motion involved, we're going to call that the negative direction. And if going downward is negative, then going upward will be considered a positive motion. All right, so if you're being pulled upward, that's a positive acceleration. If you're actually moving upward, you have a positive velocity. I'll draw all this out. Whereas to then determine the position function, S of t, of the model rocket in terms of time t. So the S of t is going to represent the position or the height off the ground of this rocket after t seconds. All right, so I'll write all this out. So again, here's the scenario. So let's say this is the ground, and they tell us that, at a height of 9 meters off the ground, right, this rocket is launched up, and then eventually it'll come back down, right, hit the ground and all that. So here's this, path the rocket takes. Now the initial velocity, all right, so they give us an initial velocity. So it's launched upward with initial velocity of 58 meters per second, right? So my initial velocity, 58 meters per second. Right? Now that's at time equals 0 seconds, right? At t equals 0, initial velocity. The only force acting on it is gravity. Now that's acceleration, right? So like again, the only force acting on it is a pull down, right? And it's being pulled down by gravity. And that's the only force on this rocket. Again, going down will be negative, going up will be positive, considered positive direction. Going down will be considered negative direction. So the acceleration, I'll call A of t, right? The acceleration at time t. And because the only force acting on this object is gravity, this is going to be that constant, right? The acceleration is, negative 9.8 meters per second squared, right? Meters per second per second. But just, A of t is always negative 9.8, right? So no matter what time is, no matter what you plug in for t, you get negative 9.8. Okay. Now, hopefully this is something where you got to recall something back from Calculus 1. So I'll put that over here. Recall that acceleration at any given time is the derivative of the velocity, right, at any given time, right? So I'll say v prime of t, where v of t is the velocity of the object at time t. Okay, so if this is acceleration, then to get velocity, we just need to integrate, right? This is just like having a little differential equation here, right? It's like having v prime equals negative 9.8, and then I integrate to get v, and it's with respect to t. Now this is a constant, so this is simply be negative 9.8 t, then don't forget plus some other constant, so plus c. Now because I'm going to do this again to get the position function, I'm going to call this c1, the first constant here. So velocity will be negative 9.8 times whatever time you're at, plus some constant c1. And also, the velocity at time t, remember that was the derivative of your position at time t, so s prime, again, where s of t represents the position. Now, position here is going to be height off the ground. Right? Position at time t. And so what we have here is another differential equation, right? We have s prime, right? Velocity is s prime. S prime equals this negative 9.8 t plus some constant. So then to get s, I integrate one more time. So s of t is, integrate this with respect to t. That'd be negative 9.8 times half t squared. Now half of 9.8 or negative 9.8 would be negative 4.9. So we have negative 4.9 times t squared, plus c1 times t, right? That's just a constant. And then plus another constant, right? So again, I'll call this c2. All right, so now I would like to find this c1 and c2 so I can complete the position function they're asking me for, right? So I need to find these constants. All right, well, we need to find these constants so that the conditions that were given to us are met. I'll write those over here. The conditions we were given was that the initial velocity, so v of 0, right? This is initial velocity here. Right? The velocity at time 0. Oops, sorry, velocity. We were told that this was, positive 58 meters per second. It was being launched upward. So I'll just say 58. You can put the units on there, meters per second, but we'll just use 58. So when t is 0, velocity is 58. Well, we can use that right now. I'll put the other condition on later. We also have an initial height, right? The initial height was 9 meters off the ground, but let's use this initial velocity to find the value of c1. Right? I'm going into the velocity function here. Right? I'm going into this. So the velocity at times, when I replace t with 0, this will be v of 0. That's going to be 58 on the left equals, and then again, replacing t with 0, you'd have negative 9.8 times 0 plus c1, and that's just c1. Right, so I have the value of that first constant. So I can write my velocity function. So velocity at any given time for this rocket is going to be negative 9.8 p plus, c1, which I now know is 58 based on the given condition. And so s of t, that would be negative 4.9 t squared plus 58t. And now I have to find this, c2 using the other condition we were given, s of 0, right? The initial height, the initial position. When time is 0, the initial position was, 9 meters off the ground, right? 9 meters. So using this, I can find c2. So put in 0 for t, so the left side will be s of 0, that's 9. Right side will just be c2. Okay, because you'd have 0 squared and then 0 here, 0 plus 0. So you got c2. So overall, so finally, the position of this rocket at any given time will be given by the following function, the following equation. Negative 4.9 times t squared plus 58t plus 9. And this is what we're going to be entering for our s of t back in the assignment. So s of t equals negative 4.9, t squared plus 58 t, then plus 9. That should be good based on the description and all the conditions that were met. Notice that the mass number had no effect on anything. So that's just a superfluous number, an inconsequential number. They're just trying to throw you off with that, right? The mass of the object being 0.09 kilograms. All right. Submit. Great. All right. Beautiful. And again, read through the answer explanations. Cool. All right, so now we have another, well, this is a different objective, but it's still very similar to what I just did with the gravity problem, the projectile motion problem. We had differential equations with some condition put on the solution. And that's called an initial value problem, right? So we're asked to find a solution to a linear differential equation, initial value problem. So yeah, initial value problems are just, here's a differential equation, and then you have conditions that are put on the solution. So you have to find the values of constants um, that will satisfy those conditions. So let's write this one out. All right, so our equation, right, the differential equation here is this. We have y prime equals 10x plus 2 times the natural log of x. And then you're given some condition on the solution, right, or what they call an initial value. We're trying to find the solution to this. So find a function y that's a function of x that satisfies this, but also satisfies this. Y of 1 equals 2, right? All this means is that when x equals 1, y has to be equal to 2, right? Input 1, output 2. So we need that to be satisfied as well by our solution. So first I'm going to find the general solution, constant there, the plus c, right? First I'm going to find the general solution to this equation by integrating. And we did this earlier in the video with several examples. So y, if that's y prime, then I just integrate with respect to x, right? The independent variable looks like x here. Integrate with respect to x. And get the general solution. So y can be anything that looks like this. The integral of 10x would be 5x squared plus 2 times, and I put this up in one of the earlier examples in the video. You can also go back to section 3.1 on integration by parts. The integral of the natural log of x is this. It's x times the natural log of x minus x. All of that is the antiderivative of the natural log. And you can do this by parts if you want, but I just know this off the top of my head, so I'm going to use it. And then plus any constant. All right, now I'll distribute the 2 here, and we get this. So here's the general solution for this equation. Y equals, like, y could be replaced by, 5x squared plus, 2x natural log of x, and then minus 2x, and then again, plus any constant. But that's not my answer. I'm not entering this. Now, the goal is to find the values of these constants, right? Find C such that, this is met, right? That y of 1 is equal to 2. When I input 1 for x, I get 2 for y. All right, so I'll write that here. Y of 1 needs to be equal to 2. So I'm replacing y with 2, so the left side's 2. And I'm replacing all the x's with 1. And we'll find this C that'll make this solution work for not only the equation, but also the condition. So we got 5 times, 1 squared plus 2 times x is 1 times the natural log of x is 1 minus 2 times x is 1 and then plus some constant. So I got 2 on the left. Now 5 times 1 squared, that's 5 times 1, that's 5. The natural log of 1 is 0, so this middle term is a 0. Then you got minus 2 times 1, so minus 2, and then plus c. Well, that's just 3 plus c over here. Subtracting 3 gives me c equals negative 1. So I pop that in here. Here's our solution. So the solution, so we go from the general solution to a specific solution. The specific solution to this initial value problem is this. Y equals 5x squared plus 2x times the natural log of x minus 2x and then plus this constant. But again, the constant that we need to satisfy the condition, the constant needs to be minus 1. Right, so here's what I'm going to be entering in my assignment. So y equals 5x squared plus 2x natural log of x. And it said to make sure that you put arguments of log functions in parentheses, right? So I got parentheses around that x after the log. Minus 2. Then after that, minus 2x, and then of course minus 1, right? That constant, the value of c that helped me get a function that satisfied the condition. Submit. Wonderful. Okay. Moving on. All right, so another one where we have an initial value problem, right? It's a differential equation with some condition that the solution need to meet, right? That the solution needs to meet. So write this out. So the equation is just a simple, y prime equals. So to get y, I just need to do the derivative, antiderivative, right? Integral. So y prime equals negative 3 pi times secant squared pi x over 4, which is the same as pi over 4 times x. Right? And then the condition that needs to be met, that needs to be satisfied is y of 8 equals negative 4 pi. So again, all this means is that when my input's 8, right, when x equals 8, the output, y must be negative 4 pi, right? So we'll use that later. So like the last example, first I'm going to find the general solution, right? We're just going to do the antiderivative of this. Y must then be, if this is y prime, then y must be equal to the integral of, negative 3 pi secant squared pi over 4 times x, dx. Now I'm not going to do a u sub this time, all right, because again, this will be negative 3 pi, right, constant multiple. Then the integral of secant squared of something is, the tangent of that thing, right? So the tangent of pi over 4 times x, but then you got to reverse the chain rule here. When I differentiate this, I'd multiply by pi over 4. So to undo that, I got to times, 4 over pi afterwards, right? It's like the reversal of the chain rule with linears inside. And then, of course, plus any constant here, and we'll do some simplification. I see, pi's cancel, right? And that's really it. Then you got negative 3 times 4. So this is the general solution of this differential equation. Y equals negative 12 times the tangent of pi over 4 times x, and then plus any constant. All right, but now I need Now I need to find this constant so that that's satisfied. I need to find the constant so that we satisfy this condition. So I'm going to do that. Replace all the x's with 8 and all the y's with negative 4 pi. So the left side has y, that's negative 4 pi, equals, negative 12 times the tangent of pi over 4, times 8. Replacing x with 8 there, and then plus some constant. Now this, pi over 4 times 8, that's 2 pi, and the tangent of 2 pi is 0. So this is negative 4 pi on the left equals, 0 plus c equals c on the right. So there's the value of the constant. Must be negative 4 pi. All right, so my solution, right, the solution to this initial value problem is the following function. So y equals negative 12 times the tangent of pi x over 4, or pi over 4 times x, and then plus my constant, but the constant needs to be, negative 4 pi here so that that condition is satisfied. Right. And here we go, right? This is what I'm going to type in, this function here. Right, so back to this. So y equals negative 12 negative 12 times the tangent of pi, we get the pi symbol, pi x over 4, or pi over 4 times x, and then minus 4 pi afterwards, right? You had the plus the constant negative 4 pi. Great. All right, continuing on. All right, so this is another one where things are falling out of the sky. You have your projectile motion like the rocket problem earlier, but this one's about a diver. So a diver steps off of a diving board at a height of 22 meters with initial velocity of 0 meters per second. So just falls off the diving board, doesn't push himself off or herself off, just initially at rest and then falls off the board, steps off the board. And again, the only force acting on the diver is gravity. And they mention the mass. It's going to be like the previous problem where the mass is not relevant. Then the gravitational constant, negative 9.8 meters per second squared, which we'll start with, right? What is the velocity of the diver after 2 seconds? So very similar to that rocket example when we're solving applications of linear differential equations. All right. So again, we're starting off with the acceleration being constant. All right, and again, the diver's falling down, you're being pulled down, so that's a negative 9.8, meters per second squared for acceleration. There's our acceleration function. And then remember that acceleration is the derivative of velocity. So for the velocity function, I just integrate the acceleration with respect to t. So that'd be negative 9.8 times t again, plus some constant, which I'll call c1, because I know I'm going to do this again in a minute. But one of the conditions that we were given was about velocity, so I can use that right now to find this constant. They told us the initial velocity was 0 meters per second. So that means v of 0 equals 0. So when t is 0, v is 0. So this is 0 on the left equals, negative 9.8 times 0 plus c1. So just c1 on the right. So that's nice. This constant here, this c1 is nothing. So we have v of t then is negative 9.8 times t plus 0. And now that I have velocity, I don't actually need to go to position. All right, remember the problem. Looking back at the problem, all they want is what's the velocity of the diver after 2 seconds. So I don't need to find the position function. So there's my velocity uh, at 2 seconds, right? T equals 2 seconds. The velocity at 2 seconds is just, negative 9.8 times 2. So that'd be negative, 19.6. 18 plus 1.6 there. And that's, of course, meters per second, which they already have there for you. So I'm just going to be entering this number, right? They already have the units of meters per second. That's it. So you're moving down, right? The diver's falling down, moving down at this rate. So velocity negative 19.6 meters per second. Right? Yeah, so I didn't need to go all the way to position function at all, even though they gave me an initial position, right? 22 meters off the ground or off the water. Hopefully it's off water. Um, so I could have gone and found the position function, but all they asked about was velocity, right? Great. All right, this is verify a solution to an initial value problem. So we've seen something similar to this before, where we're given a function. All right, so here y equals 3x cubed plus 4x minus 4. And we're asked to determine if that's a solution of the equation below, but also an initial value problem. So you also have a condition that needs to be satisfied. So two things need to be satisfied: the equation and the condition. All right. Now I'm going to check the condition first because I think those are the easiest to check. There's plugging in numbers, and then we'll check if that's satisfied, then we'll check the equation. If the condition's not satisfied, then you don't need to check the equation. You don't have a solution to the initial value problem in that case. So again, here we have, this question is, the following function, y equals 3x cubed plus 4x minus 4, a solution of the initial value problem. Now you'll see a lot of times they'll abbreviate initial value problem as IVP. So you have a differential equation, right? DE, again, usually DE will represent differential equation. So the equation we need to satisfy is this, y plus 1 needs to be equal to 3x cubed minus 18x squared plus 4x plus 2y prime, and then minus 11. All right. And then you have a condition, or sometimes referred to as this initial value. And the condition that needs to be met is the value of y, and again, the variable independent, the input variable here is x. The value of y at x equals 0 needs to be negative 4. All right, so I'm going to check the condition first, because again, I think those are the easiest to check. And if the condition isn't met, then you don't have to worry about the equation, right? You won't have a solution. Now, if the condition is met, then we need to check to see if the equation is also satisfied. To check the condition, so I'm plugging in negative 4 for y, so we have negative 4 on the left, equals, 3 times 0 cubed plus 4 times 0 minus 4. Well, that is also negative 4, right? You'd have negative 4 equals negative 4. That's good. All right. So the condition is met. Wonderful. Now I need to just substitute into the equation and see if the equation is also satisfied. Right now we have y. put that in for y. I just need y prime over here. The simple polynomial, right? Y prime be 9x squared plus 4. So this is going to go in for y prime here. All right, so now let's check the equation. Right, so on the left we've got y plus 1. So that'll be 3x cubed plus 4x minus 4. All right, 3x cubed plus 4x minus 4, right? There's y, and then we're going to add 1 to that. Really, I don't need parentheses around this because it's not being raised to any powers or multiplied by anything, but we'll simplify that in a second. And on the right side, you got 3x cubed minus 18x squared plus 4x, and then plus 2 times, and then here's where I replace y prime, right? Y prime be 9x squared plus 4. And we're going to distribute this 2, multiply the whole thing by 2, and then minus 11. All right, so after simplifying, left side, you got 3x cubed plus 4x, and then minus 3, right? Negative 4 plus 1. On the right side, you got 3x cubed. There'd be no other x cubes. Then I have this minus 18x squared plus 18x squared, right? 2 times 9x squared. So that'd be nothing. There's no x squareds. Then I have 4x, and there'd be no other x terms, right? So plus 4x. So far, it's looking good, right? And then the constant terms, you got 2 times 4 is 8, minus 11. 8 minus 11 is negative 3. Check on that. Both of these are the same. So the answer is, yes. Right? This function that we were given satisfies both the equation and the condition, from this initial value problem. Great. So back here, I'm putting yes. Wonderful. All right. Now they're checking the equation first and then check the condition. But again, I like to check the condition first this is just a bunch of number plug-in. All right. So yet again, we are given, is the function we're given a solution of the initial value problem, right? So does it satisfy the equation? Does it satisfy the condition? All right. So let me write this out. So is the following function, right, we got y equals the cosine of pi, it's pi x over 2, that's pi over 2 times x, and then afterwards minus 4, a solution of the following initial value problem. Right. Now the differential equation we're given, we got the opposite of y prime, so negative 1 times y prime, plus 2 times the cosine of pi over 2 times x, or pi x over 2, then minus 12, that's the left side, equals negative 2y plus y prime plus 4. So there's the equation, and then we have the condition that needs to be met. The value of y at x equals 0 must be negative 3. Right, so I'm going to do this first. Right? I'm going to check the condition first. And if that doesn't work out, then we can say no. And if it does work out, then we have to go and check the equation. So y is negative 3, right? Left side is negative 3, and then, cosine of 0, right? Because x is 0, pi over 2 times 0, minus 4. Remember, the cosine of 0 is 1, so this works, right? You got negative 3 on the left, negative 3 on the right. Okay, so the condition is met. Great. Now, does it satisfy the equation? So I've got y. That's going to go here where this y is. But there's a couple instances of y prime, right? So I need y prime. Now this would be, remember the derivative of cosine of something was negative sine of that thing, right? So negative sine of pi over 2 times x. But then times the derivative of the thing inside, which would be pi over 2, right? So, and then your derivative of negative 4 would be nothing, right? So here's y prime. That's going to go in here and here, right? And then y is going here, right? So let's make these substitutions. So the first term over on the left side, you have the opposite of y prime, so it'll be positive pi over 2 times the sine of pi over 2 times x. And then we got plus, plus 2 times the cosine of pi over 2 times x. And then minus 12. All right, so that's the left side. Right side, I've got negative 2 times this. All right, now you'd have to distribute the negative 2, okay? So it's negative 2 times all of y. So negative 2 times cosine of pi over 2x. Pi over 2 times x. It's pi over 2, sorry. And then negative 2 times negative 4 be, plus 8. All right. And then plus y prime, right? So that'd be this. So minus pi over 2 times the sine of pi over 2 times x. And then you got plus 4. Right. Now 8 and 4 make 12. So pretty much what I've got here is these are opposites. They're not the same. Now on the left side, you got positive pi over 2 times the sine of pi over 2x. You got the opposite of that on the other side. You got left side positive 2 times the cosine of pi over 2x. You got the opposite of that on the right side. And then negative 12 on the left side, positive 12 on the right. So these are opposites. They're not the same all the time. So no. Okay, the doesn't satisfy the equation. All right, the answer is no here. All right, so back here, answer is no. Does not satisfy both the equation and the condition. Great. All right, moving on. All right, so this time we're given an equation and a condition, right, an initial value problem, and asked to find the solution ourselves, right, not just verify it. We've done one of these or a couple of these already. So I'll write these out. So the equation is this, y prime equals negative 4x plus 6 times e to the 3x. And the condition is the value of y at x equals 0 must be positive 4. And so when x equals 0, y must be 4. Now, if this is y prime in terms of x, then y will be the integral of this. So I'm just going to do the integral. The integral of negative 4x would be negative 2x squared. And then 6e to the 3x would be 6e to the 3x again, but then times a third. So plus 2e to the 3x. And then, of course, plus some constant, right? So I'll write out that I integrated here, right? So integrating with respect to x. So there's the general solution of this equation, right? Y could be anything that looks like this. But now I want to find the value of this constant, this c, so that the condition is met, right? So now here's the condition, right? I'm replacing all the x's with 0 and the y's with 4. 4 on the left equals, this would be 0, negative 2 times 0. Now e to the 0 is 1, so this is still 2 here, this plus 2. plus c. So the value of the constant must be 2, subtracting 2 from both sides. So our solution then is y equals, negative 2x squared plus 2 times e to the 3x, and then plus your constant, which has to be 2 to satisfy that condition. And there we go. That's what I'll be entering. So y equals negative 2x squared plus 2 times e to the 3x power, and then plus 2, plus that constant 2. Great. All right, moving on. All right, so this time we're asked to identify the graph of the particular solution to the differential equation shown below, right, with this condition. So we have an initial value problem, right? Y prime or dy over dx, first derivative equals some function of x, right? So I'm just going to be integrating to solve that. And then we have to find the value of the constant that'll help us, that'll give us a solution that satisfies this condition. And they say drag the red point initially placed on the left side of the graphing window to the correct solution curve of the above initial value problem. Okay, well, they all look pretty similar now. So I don't have to solve this. All right, you can. It's not hard. This is just a polynomial in x. So this would be really easy to integrate, and then you could easily find this, the value of the constant that satisfies this condition. But just pick, all these solutions are the same shape, right? Just they only differ by a constant, right? They're just shifted up or down. So we just need the one that goes through the point 0, -1, right? You see y of 0 equals -1. So when x is 0, y needs to be -1. So I'm dragging this point to this curve here, right? See how that goes through 0, -1? So that's got to be the solution curve they're talking about. So this is a very, very simple problem. Hooray. So just make sure you're, picking the one that satisfies the condition, goes through the point that they mentioned. Now they actually go through and solve the thing. Right? You don't need to. All right, so here we actually have to solve something. All right, one of these initial value problems again. So you're given a differential equation and then some condition that needs to be met. All right, so again, we'll solve the differential equation, find the general solution, and then find a particular solution, that satisfies the condition. So the equation we're given is dy over dx. I'm just going to write y prime, right? It's first derivative of y with respect to x, equals negative 4x cubed plus 4x. All right, so I'll first solve this and then I'll write the condition. So I'm integrating, this is y prime in terms of x, so all I'm going to do is integrate here. I'll just put int. And if I integrate this with respect to x, this would be a negative x to the fourth plus, and then 4x when you integrate would be 2x squared. And then, of course, plus some constant, right? So there's the general solution of our differential equation. Now I want to find c so that the following condition is met. Y of 2 needs to be equal to -4, right? Let's see what that looks like, right? So this is telling me when x is 2, y is -4. So I go through my general solution here, replace y with -4 and all the x's with 2, and we'll find this c. So I got -4 on the left equals, the opposite of 2 to the fourth plus 2 times, 2 squared, and then plus some constant. So that's -4 equals, this would be -16 plus 8. So that's -8 plus our constant. And then adding 8 to both sides, we get, c equals 4. Right. So what I'm going to enter here is this. Y equals negative, x to the fourth plus 2x squared plus 4. All right, that's the particular solution that would satisfy the condition. So y equals the opposite of x to the fourth power plus 2x squared, and then plus 4, right? That satisfies both the equation and the condition. Great. All right, so 2 more objectives to finish off. All right, so we're back to the gravity stuff. So this time it's about a soccer ball being kicked upward instead of a rocket or instead of a diver like in previous examples, right? But it's just a projectile motion problem where only gravity is being considered. So a soccer ball is kicked upward from a height of 1.6 meters. So there's our initial position, right? Position at time 0, with initial velocity of 22 meters per second. So there's our initial velocity. And notice it's positive, right, because it's kicked upward. And the only force acting on it is gravity. Again, don't worry about the mass of the object here. We're going to start off with this gravitational, constant, this acceleration function, negative 9.8 meters per second squared. And we're asked to simply determine the position function of the ball, right? How high off the ground is the ball at any given time. Right, so like all those other problems we've seen in the other couple examples, we're starting with this acceleration at any given time is negative 9.8, right? And the units on acceleration is meters per second squared here. Then I integrate to get velocity. Right? So velocity would be negative 9.8 times t plus some constant, which I'll call c1. And they told us something about the velocity, right? The initial velocity, right, v of 0, the initial velocity was 22 meters per second. Right? Again, this will be meters per second for velocity. Well, if I plug this in to my velocity function here, can you see how c1 must be 22? Because, you plug in 0 for t, this will be 0. This negative 9.8 t, that'll be 0. So you'd have c1 equals 22. Right, so there's the value of c1. So here's our velocity function now, negative 9.8 t plus 22, meters per second. And then to get position, I integrate one more time, right? So s of t would be negative 4.9 t squared plus 22t, and then plus some other constant, right? I'll say c2. And we're given an initial position to help me find this c2. Right? The initial position, which I'll say is s of 0, right? The position at time 0, they said it was 1.6 meters off the ground. This will be in meters, right? Now again, we can plug in 0 for t. That'll make this term 0, this term 0. And we'd see that C2 must be 1.6, right? C2 must be 1.6. So I'll just scratch this off and put in 1.6 here. And here we go. There's our position function. The height of the ball off the ground at any given time is given by this function here. Type that in. So negative 4.9 t squared plus 22t, and then plus 1.6. 1.6, not 1 divided by 6, 1.6. All right, submit. Great. And this is just like the others. In fact, this is just like the diver question from earlier where, the initial velocity is 0 meters per second, so it's starting off at rest. Initial height is 22 meters, but they're only asking about velocity here, right? See the final thing, they're only asking about the velocity of this ball. So a ball is released off a platform at a height of 22 meters with an initial velocity of 0 meters per second. The only force acting on the ball is gravity, right? So we're going to start off with that acceleration being negative 9.8 meters per second squared again. Ball has a mass of who cares, and then what is the velocity of the ball after 2.5 seconds? So same start as all these other projectile motion, falling bodies problems where only gravity is concerned, right? So acceleration is once again starting off as negative 9.8, meters per second squared. You integrate to find velocity function, right? Velocity is negative 9.8 t plus some constant, right? I'll call it t1 again. But they tell us that the initial velocity, right? So v at 0 is 0, and this will be in meters per second for velocity. And this means that c1 is 0, right? If I replace t with 0, you'd have 0 plus c1 on the left and 0 on the right for the velocity. So c1 is 0, so I don't need the c1 here. So there's my velocity function. And then they're asking us, what's the velocity at 2.5 seconds? Right, 2.5 seconds. So the velocity at, 2.5 seconds is negative 9.8 times 2.5. Now negative 9.8 times 2 would be negative 19.6. And then, half of negative 9.8 would be 4.9. Putting these together, that's negative 23. And then you put 1.5 on that. So negative 24.5 meters per second would be how fast the ball is going downward at the 2.5 second mark. Double checking my arithmetic here. Right, so velocity is, negative 24.5, right? And they've already got the units there. They've already got the meters per second. So I'm just entering this number. Wonderful. All right, so that objective with all the, starting off with acceleration, moving to velocity, moving to position by integrating, and given some initial conditions, right, that objective is done. Right, so just got one more to finish off with, which are more of those initial value problems, right? But it's just the ones where you have to verify. So we've seen a couple of these now, right, where you're given a function, y is a function of x again here, and then you're asked, is this a solution to the initial value problem? Does it satisfy the differential equation as well as the condition given? Okay, so back here. So yeah, so the question is, is y equals 3x minus 3 plus e to the negative 3x? Is this a solution of the following initial value problem, right, IVP? Right, so the equation we need to satisfy is, y prime equals 3x minus y, then minus 2 e to the negative 3x. And the condition that needs to be met is, y of 0 must be negative 2, right? So again, I like to check this first. It's the easiest one, easier of the two to check. So when x is 0, y must be negative 2. So let's see if that happens in our function here. So negative 2 for y, so negative 2 on the left. Is that equal to, 3 times 0 minus 3, and then plus e to the negative 3 times 0 power? Replacing all the x with 0. So that's negative 2 equals, 0 minus 3, and then plus 1, right? Remember, e to the 0 power would be 1. And that works, right? That's negative 2 equals negative 2. Okay, so far so good. The condition is met. So now the equation. Right? So I've got y. That's going to go in here for y. I just need y prime then, right? So substitute y prime. So if that's y, right? If that's y in terms of x, then y prime with respect to x would be 3, and then nothing, and then, minus 3 e to the negative 3x. That'd be e to the negative 3x, and then times the derivative of negative 3x, right? So there. So this is going in for, y prime on the left here. So I make those substitutions. The left side, we have 3 minus 3 e to the negative 3x. On the right side, we have 3x minus, and then all of y, right? So this y, this 3x minus 3 plus e to the negative 3x. And then we have afterwards minus 2 e to the negative 3x. And I'll simplify this by distributing the negative here and combine like terms. So left side is still 3 minus 3 e to the negative 3x. Now the right side, you'd have 3x minus 3x. So those are gone. Then you got minus negative 3, that's positive 3. And then negative e to the negative 3x. But then you'd have negative e to the negative 3x, and then minus 2 more of e to the negative 3x. That'd be minus 3 e to the negative 3x. And look, the expressions on both sides are the same. So the answer is yes. The function we were given does satisfy both the equation and the condition from this initial value problem. So answer is yes. Wonderful. So another one where we're asked to verify, or that's the only objective left. So I feel like, this is going to be it here. Verify the solution to an initial value problem. So just like the last example and several others we've seen. So is the following function, y equals the natural log of 4x squared, is this a solution of the following initial value problem? All right, so the equation is this, negative 2 y prime minus e to the 4x power plus 1, all right, so that's the left side, equals negative x, or the opposite of x, plus 2 times e raised to the y power. All right, so there's the equation. Now the condition that needs to be met is this. The value of y when x equals e divided by 4 is equal to the natural log of e squared over 4. So again, easy check. This condition's the easier one to check, right? So I'm replacing x with e over 4 and y with the natural log of e squared over 4. So the left side, y becomes natural log of e squared over 4. Is this equal to the natural log of 4 times, and then here's where I'm replacing, I'm replacing x with e over 4. E over 4 squared, right? It's x squared. And yeah, these would be the same, right? Because this is natural log of, 4 times e squared over 16, but 4 goes into 16 4 times, so it's just e squared over 4. So yeah, they are the same thing. So the condition is met. Now I'm satisfied. Now I'm seeing if it satisfies the equation, right? So there's y. That's going to go in for the power y here, right? E to the y power. Now I just need y prime, right? So y prime, where the natural log of something is 1 over that thing, the derivative, times the derivative of the thing inside would be 8x. And if you simplify this, 8 over 4 is 2, x over x squared would be 1 over x, so that's 2 over x. So this 2 over x is going to go in for y prime. All right, so let's substitute this stuff. Do it here. So on the left side, we have negative 2 times 2 over x. So that'd be negative 4 over x. Then minus, e to the 4x plus 1. There's the left side. And then the right side would be negative x. So I'm kind of seeing right now that they're not going to be the same. I don't see any negative x over here, but plus 2 times e to the y. Remember, e to a natural log, they undo each other, so I'd be left with 4x squared. So this is just 2 times 4x squared. That's plus 8x squared. And yeah, these are not the same expression for any x, right? They're not the same value. So no. All right, the answer this time is no. The function we were given is not a solution of our initial value problem. Okay, great. And it looks like I've completed that and therefore completed this preview version of this assignment. Wonderful. All right, so there you go. Some pretty basic introduction here to some simple first order, for the most part, differential equations. Now, as I said at the top of the video, the questions I saw here may not be the same questions that you see when you work on the assignment yourself, but all the objectives are the same, right? And so hopefully the problems are similar enough so that when you work on the assignment yourself, watching me helps you a little bit. All right, and thank you very much for watching.